CIVL Civil Engineering, CIVL202 Statics. This video is on Learning Objective 3.5, discussing internal forces. As a reminder, today is the best day to learn statics because we'll be using this a lot, particularly in mechanics of materials and structural analysis. We're moving into a new section, so we're going to keep using our force vectors, particle equilibrium, force systems, centroids, and rigid body equilibrium as we go in to talk about internal forces. So when we approach an internal force problem, we're going to do our rigid body equilibrium to determine the external reactions so that we can then look at the internal force systems. So with that in mind, we can put some notes on the board about internal forces. So internal forces are going to be those forces and moments that are inside a member. Inside a member, MBR for member. So forces and moments inside a member, and when we do this, we're going to use something called positive beam sign convention. Now, positive beam sign convention is to be delineated from a global sign convention. So up to this point, we've talked about our global sign convention. Typically, we're going to say something like X is to the right, Y is up, and Z is coming out of the board, something like that, our global coordinate systems. But when we talk about positive beam sign convention, what we're looking at is the sign convention for how we talk about these internal forces. And so we're going to use both when we do internal force problems. So we need to make a clean distinction between those two categories. So this is what describes or defines our internal forces. Defines our internal forces. In order to do this, we're going to use something called the method of sections to talk about internal forces. So when we've done all of our statics work up to date, we've been able to talk successfully about external forces, and we want to continue to do that, but our equations of equilibrium, our free body diagrams, those talk about the forces acting on the outside of the body and allow us to analyze them that way. So we can't see the internal forces, they actually cancel each other out. What we do with the method of sections is that we cut the member, making what was internal forces external. So if we want to know what's going on inside a body, the obvious thing to do is to cut it open. So for example, this might be how if there was a big box of jelly donuts and you like jelly donuts, but there's particular flavors you don't really like, well, what would you do? Now, some of you might, lift up the donut and poke a hole in the bottom, and then if you didn't like it, put it back, but that's kind of rude. The nicer thing to do would be to get a knife and cut them in half, and then you could see what the inside filling is. And that's exactly what we're going to do when we think about these members. Now, obviously, we're not going to cut the physical members apart, although I may do that here in just a moment. The idea is that we're going to cut them analytically, expose those internal forces, draw a new free body diagram, and then write our equations of equilibrium where those internal forces are now external so we can see them. We basically have already kind of done this with our analysis of frames where we take a joint, we pull the pin, and then we can see the forces that were previously inside that pinned joint in a frame. So it's the same sort of idea. Now, turns out that in 2 dimensions, there are 3 flavors of internal forces. And it's 3 different ways that the forces interact with the beam. So the first one you actually already know about. It's going to be a normal force. Normal force sometimes called an axial load, sometimes called thrust. Okay, all of these are valid ways to think about this. And when we look at those, the idea is that these are going to be along a member. So that's the axial part, perpendicular to the cut we're going to make to expose those internal forces. So along the member, perpendicular to the cut. And so the idea is that if I have a member, so like you can see my rope here in tension, if I have this member and I were to take a knife and I want to see what's happening inside of that member, I would go through and I would cut it. Now when I cut it, the ropes obviously fall, right? And what we're trying to do is we're trying to say, okay, I've got a member and I've cut it in half. And now in order to keep it in equilibrium, just like we did with reactions, I have to identify, well, what was the force that was going on to keep this in an equilibrium, right? So I'm leaving the reactions over there by the frame over here in place, and I want to keep pulling. And so I'll draw a force here, like so, right? And it turns out that if I look at the other rope, it's going to have the same force, right? But acting in the opposite direction. So Newton's third law again, like so. So hopefully this makes sense to you. So we've cut it open, and this is going to be our, what do we call this? We call this tension. So tension, sometimes we'll indicate it with a T in parentheses, and we're pulling on each member. And tension is going to be our positive, remember positive beam sign convention? This is going to be positive. So the idea is that when we cut a member open and we expose the normal force, which we will typically indicate with an N, so we would say N, tension, positive, right? We're going to assume it's in tension. So we're going to assume it's in tension, and then if we guess wrong, we'll get the other case, which would be, so we cut it open, and what we get instead is compression. Which would indicate with a C, and this is pushing. Now, obviously, we wouldn't want to push a rope, but if we're cutting across a part of rigid member, then there's no problem with that. So our arrows would go this way, and this would be our normal force, compression, and it would be negative. Okay, normal force, compression, negative. So tension is positive, compression is negative. Now, remember that distinction between our positive beam sign convention and the global sign convention that we might have up here? Well, both of these arrows are considered to be tension, so positive normal force. But if I were to do a free body diagram of this side of the diagram, the positive normal force would also be in the positive x direction in this case. But on this side, if I were doing this diagram, the positive normal force is actually going to be negative in the global sense. So when we put that positive normal force into our equations of equilibrium for the right side, it's going to go in as a negative N, negative normal force. All right, so we got normal forces, push or pull, along the member. My cut goes this way, so it's perpendicular to the cut. So if we've got one that's perpendicular to the cut, we can also talk about shear. So a shear force, is going to run parallel to the cut or perpendicular to the member. Parallel to the cut or perpendicular to the member. Okay? And so the idea is that, hopefully everybody knows what these are. Everybody know what these are? If you said scissors, you're wrong. These are shears, right? And so if I were to take something like I've got a block here. If I were to try and cut it to expose the internal forces, right? I'm going to see where I'm going to have a force on the blade up here, and I'm going to have a force on the blade down here, and they're very, very close together, and so they're going to shear the member apart. And so the idea is that if I were to have my member there, I'm going to have one force on one side, and then just a little bit away from it, I'd have that second force. So those are my two scissor blades, right? My shear. And when it cuts it apart, what we get would be the shear force across the cut, right? Parallel to the cut face, perpendicular to the member. It looks like that. So on one side it's pointed down, on the other side it's pointed up, because when we add them back together, close up that cut, they're going to go to zero when they go back to being internal forces. And so the idea when we shear something, you can see what I'm doing here with my yardstick, is that I'm going to push down with one hand, right? And I'm going to lift up with the other. And that's going to be what my shear is trying to do. So I'm putting a lot of shear right there close to the connection. That's pure shear. So shear is going to show up this way. Now, in order to identify our shear positive direction, we're going to use our right-hand rule. So remember our right-hand rule about the cut. Right-hand rule about the cut. So if I've got the cut, the idea is I want to use my right hand, and I'm going to reach over and I'm going to grab the beam and I'm going to try and pull it shut, right? And in this case, my fingers point in the direction of the shear. You see that? My fingers are down, the arrow is down, and my thumb is out of the board, and so that's positive. If I use my right hand and I come from this side and I try to go grab this beam, same thing. I grab it, my fingers are pointed in the same direction of the arrow, and my thumb is out of the board. And so we would indicate that this way as positive shear. So we use the symbol V for shear. N for normal, V for shear, and that's a capital V. And so that's my right-hand rule. It looks like this. So again, local case, our positive beam sign convention says that I'm going to use shear, right-hand rule about the cut, my positive, right? Okay, on the two different sides. Right-hand rule about the cut. But when I use my equations of equilibrium with the global sign convention, it would be negative on the left-hand side of the cut and positive on the right-hand side of the cut. This naturally means that our negative shear is going to be the opposite direction, meaning got my shear force there, my shear force there, and my shear is negative. And I know this because if I use my right-hand rule, if I roll my fingers, reach over and grab the beam, roll my fingers up, my thumb's now pointing in the direct into the board, so negative, right? Same thing over here. If I reach over to grab that beam and my fingers point in the direction of the force, so they're pointed down, my thumb is into the board, and so that's going to be negative shear. So positive beam sign convention, we've talked about normal force, tension positive, so pulling, and shear force, which is going to be parallel to the cut or perpendicular to the member. It's the right-hand rule about the cut to give us that positive. Cool? So both of those are going for us there. Now, from there, we've got one more mode, so that's 1, 2. We have a third one we can talk about. Go ahead and erase this guy. Again, remember, this is still positive beam sign convention. Even though I'm erasing it, it's still what we're talking about. We'll talk about bending moment. Bending moment. Okay, so bending moment creates bending in the member. Okay, so the idea is if I take my yardstick here, I can show you bending moment in the middle because it's going to cause bending. Y'all see that? So it bends. Okay, so that's what bending moment's going to cause. And so our beam, our member here, is going to tend to want to bend like so. And looking at that cut, the way that we'll think about that is in order to get that bend shape, I'm going to have to put a applied moment inside that causes it to bend. So you see my little member here, and I can bend it, right? So in order to get it to curve like that, I got to bend this way. So this hand represents that internal bending force. It's causing it to bend. Bending moment, I should say, sorry. And so it's curling this way. You'll see that? But over on this side, it's going to curl like that. So again, in terms of our global sign convention, we've got two different values. But in terms of our internal positive beam sign convention, this is positive bending moment. And the reason you know it's positive is because the beam is positive. You know the beam is positive because it's smiling. So a happy beam is positive beam. So you can see it smile at you, right? And so we see it curl up, right? And it smiles, curl up, and it smiles. Even though this would be positive in your sum of the moments, it would be negative in your sum of the moments in the global sign convention. These are both positive moment in my internal positive beam sign convention. Naturally, that means that your negative bending moment is going to cause the beam to turn down and frown at you like this, right? So that's going to be negative moment with a capital M for our moments, capital M. Okay. Now, the technical way that we talk about this is not happy and frowny beams. What we would do instead is we'd actually look at whether the top of the beam is in tension or compression. So if I look at this and I've got these parallel lines, if something goes into compression, they're going to crunch up. If it goes into tension, they'll widen out. So when I bend it like this, you can see where I kind of smush them all together there at the top. The top's going into compression. The bottom's going into tension. It's getting a little longer because it's experiencing positive bending moment. And so our tension on bottom, compression on top. That's how we know that that's the technical definition. And so if we show negative bending moment, we'll flex it like this and we get tension in the top, so it's getting longer across there, and it compresses on the bottom, and so that would be negative bending moment. So that's how we're thinking about that. Tension on the bottom, compression on the top. A happy beam is positive, and we'll draw our internal moments like that. So we've got these three things, but it turns out that very rarely normal force happens sometimes. Our ropes are great examples where we have pure normal force. But when we're looking at beams, most of the time we have a little bit of all of these. And so if we're to combine this all together, our combined loading, when we cut our member apart into two pieces, right, to expose those internal forces, and I draw my positive beam sign convention, I'm going to have my normal force pulling. I'm going to have my shear force perpendicular to the cut, and that's using my right-hand rule about the cut. So I go grab that beam, pull it over to try and close up the cut. My fingers point in the direction of the arrows with my thumb coming out. So those are the same magnitude, shear force. And then I'm going to have my positive bending moment that's going to tend to want to cause the beam to smile. And so that's our combined total force. Sweet. So our combined case. And so often what we would do if we're doing an internal problem like we'll do during class, we'll cut the member open at the location. We'll draw these internal forces on one side or the other. And then we will write our equations of equilibrium for one side or the other and solve for the three unknowns at the cut. I'll add there's one more type of moment. This is for 2D, but in 3D, we'll have two shear forces and two bending moments, and we'll also have something called torsion, which is very interesting to my mechanical engineering students. Torsion is going to be an indication of twist along the member. And when we twist something along the member, we'll use our right-hand rule again to indicate the torsion. So if I have my meter stick, I can actually twist my meter stick, right? And so I'm applying a moment, but it's a torsion that I'm applying as it twists along the meter stick. All right. So just to sum up, internal beams, we're using our positive beam sign convention. We've got normal force where we've got tension pulling. We got our shear force. We're using our right-hand rule about the cut. And then we have our bending moment where happy beams have tension on the bottom, compression on the top for positive beam sign convention. We'll put them all together when we do our internal force problems. And then when we talk about 3D, we'll revisit this torsion issue just very briefly. I hope this is helpful to you. Please have a discussion about it, and we will see you in class.